Hello, the purpose of this video is to go over a proof of the Pythagorean theorem. Now, let's say you have the length of two edges of a triangle, like you have this length and you have this length, and you want to find the third length there without having to actually measure it. There may be many cases where you may need to find that third length without having to actually measure it. You may need to, it may be a ladder against a wall. There may be the length across a pond where you could actually find this length and this length, but that across the pond would have to be stretching a tape ruler across the whole pond. Things that couldn't happen that way. So it'd be nice to be able to find this third length if you know these two lengths. Well, to do that, we have to have some sort of formula to do that. And there is a formula, and it is Pythagorean theorem. And here's a proof of that Pythagorean theorem. Let's say we have this right triangle, okay, and then we're going to take draw a square, okay, and we're going to put this right triangle into the corner of that square. Then we're going to take another copy of that same triangle and put it in the corner there. Same triangle, put it here. Same triangle, put it here. So the length of this triangle, the width, the one of A, call the one leg B. The other leg we're going to call it C. When we put that triangle, when we put that triangle in here, this length is still A, this length is C, this length is B. And if they're the same exact triangle all the way around, then we're talking about A, B, A, B, A, and B. And the other parts here being C, C, and C. All right, so now let's think about it. Now this square right here in the center, the area of that square is a c squared. If I rearrange those triangles, and I do it like this, I move this one here, and this one here, and move this here, and this, oops, triangle, not that triangle here, I'm going to end up with two rectangles here. Actually, squares. The length and width of this is going to be B. B is this length here. B is also this length there. And this length and width are going to be A. Because remember, the length of this side was B plus A. This part's B, this part's A. This is A, so this must also be A. If this is A and the whole thing's A plus B, then this must be B, and so on the line there. So the area in here is B squared, the area in here is A squared. And if these are the same four triangles, and they took up the same space inside of that same square there, that means that A squared plus B squared is equal to the area of that original square, which was C squared. And there is your proof that the sum of the square of the legs of the triangle, sum of the square of the legs of a right triangle equals the square of the hypotenuse. Now that's one way to prove it. Another way to look at it is going to be on the next slide here. Okay, this proof is pretty much the same as the previous. However, it does work more with equations rather than the visual part there. Let's say we have that rectangle. We have this rectangle that was formed by taking a right triangle, 4 copies of it, setting it up just like we did before. The length of the edge of this rectangle, the length of this edge is a plus b, the length of this edge is a plus b, so the square's edges all have a length of a plus b. The area of the square inside of the square, the little square, is c squared. Length times width, c times c squared. The area of each triangle, the area of each one of these little triangles would be 1/2 base times height. Base and height are a and b, so it'd be 1/2 a times b. But we don't have just one triangle, we have 4 triangles. So we would multiply that by 4, and the area of the 4 triangles altogether would be 2ab. So that would be the area of all 4 of these triangles added together would give you that 2ab. Then you have the area of the big square, which would be the side times side, which would be the a plus b times a plus b. You do a little FOIL action here. First times first gives you a squared. Outer gives you ab. Inner gives you ab. The last gives you b squared. You end up with the area of the big square being a squared plus 2ab plus b squared. Now, if that's the area of the big square, then the area of the small square, which we know is c squared, would be the area of the big square minus the area of the triangles. These are the 4 triangles. And the area of the 4 triangles was 2ab. So if we subtract that 2ab from the area of the big square, we will get the area of the small square. And the 2ab's will cancel, leaving you with, dun, 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 your Pythagorean theorem again. A squared plus b squared equals c squared. Okay, there is another way to prove the Pythagorean theorem where if you take a triangle, draw any old right triangle, and you make 3 unit or any kind of unit length along the edge there. Like this one, I chose this square to be 1 unit, and I chose this one was 3 units wide and 4 units high here, and it doesn't matter whether this is units, centimeters, inches, feet, as long as they're consistent and it's a square. It doesn't matter if it matches up to 3 and 4. It could be any kind of squares set up there. But you're going to find that if you take these squares and you move them and you line them up over here, so that they form another square out here with a bunch of little squares inside of it, you'll find out that this one's going to form a 5 by 5. This is 3 by 3. This is 4 by 4. The area here plus the area here adds up to give you that area here. Unfortunately, I don't have any way of drawing those sideways angled squares to be able to do this properly here.